Hi, my name is Kevin Stewart.
And my name is Rola Jawed, and another group member that's not with us today is Ting Ye. And what our objective is for this C380 project is to develop a GUI that calculates the steady-state temperature in a plate given boundary conditions and external heat sources. And the features that come with the GUI is it should handle any plate configuration that's provided by the user, and also boundary conditions. And the GUI should at least read a text file with plate configuration boundary conditions, and I have a drop-down list with most common materials for other heat conductivity K-values. And the ultimate goal for this project is to determine the heat flux within the plate of the chip. And here's Kevin explaining the code.
All right, so as you can see on the screen, the first thing we're given from the consumer is our text file. The text file will look something like this. This is the boundary for that text file. The first four columns are the positions, the X and Y positions. The fifth column is the actual boundary itself, and then the sixth column is the value for that column, or for that actual row for that boundary. So once we're given the boundary condition, we can actually start creating our position matrix, which then in return, that actually produces our A matrix. And from our A matrix, that's set up using a system of linear equations using the center difference, the forward difference, the backwards difference, and we do that in order to calculate the flux throughout our chip. Luckily for us, it's a steady state system and it's homogeneous, so that makes the whole problem a lot easier. So basically we just have to calculate the flux using all these systems of linear equations, and from that we can use, once we get our A matrix, we can use Cramer's rule, and from that we actually get our B matrix, which the B matrix shows the actual temperatures of each given node, which is created by the boundaries that the consumer gives us. So now we can actually run the GUI, and the first thing that pops up is this screen, and you're prompted to load the text file. You can load any text file that you'd like, and once you load it, you enter the change in X value, and then you can pick your material. You run it, and ours takes a little while to run because we have two figures. The first figure is going to plot the temperatures on each node, and the second one's going to plot the actual, they're called quivers. It shows the direction of the heat going from high temperature to low temperature. As you can see, it's hotter on the edge. Same with over here, you can see the numbers are all greater, and it gets colder as it goes towards the actual, this is actual constant temperature in this chip. Once you do that, you can save your file, come over here, and it's called nodes.txt, and then this actually shows you the temperature at each different node for that boundary. So now we can run it again and say we'll reset it. If the user wants to input their own k-value, they can click on other k-value, then this screen will be editable. Say 200. Run it, and then of course wait for it to do all of the behind the scenes for the code, and then again it'll produce the figure of the chip itself with the temperature on each node, and then the direction vectors showing the flux, which is the change in temperature going from high to low. As you can see, this is the constant state, the constant temperature of that chip again. You can save the file again, come here, and this will be the temperatures for each given node. And I think that about wraps it up for our project.